Trigonometric substitution. First, let's talk about what is trigonometric substitution. Let's suppose you have an expression, the square root of 9 minus x squared. We know from algebra that you cannot separate this radical to simplify it. So this is not true. If you factor the inside, you get the square root of 3 minus x times 3 plus x. And this also doesn't help us simplify. So what can we do to simplify it? Well, what we can do is make a trigonometric substitution. Let's see what happens if we let x be equal to 3 times the sine of theta. If we substitute 3 sine of theta in for x, this expression becomes the square root of 9 minus the quantity 3 sine of theta squared. From here, we get 9 minus 9 sine squared of theta. So all I'm doing here is squaring each part of this. And then we can factor out a 9 on the inside of the radical. And when we take that out, we get 1 minus sine squared of theta left over. But we know that 1 minus sine squared is equal to cosine squared. And so this expression becomes the square root of 9 times cosine squared of theta. And now, because this is multiplication right here, we can separate this radical into the square root of 9 times the square root of cosine squared. And the square root of 9 is 3, and the square root of cosine squared is the absolute value of cosine. So what have we done here? Well, we got rid of the radical. And sometimes it's really important to be able to get rid of a radical. So this type of substitution is extraordinarily useful when finding antiderivatives of certain types of functions. Before we get into the guidelines for how to make trigonometric substitutions, let's talk about inverse substitutions in general. So we know from the substitution rule that if you have the integral of f of g of x times g prime of x dx, we know that we can let u be equal to g of x, and then du will be g prime of x times dx. And then this integral becomes simplified into f of u times du. So this is the process that we think of as u substitution. And this type of substitution is useful when you have a known composition function with the derivative of the interior function available in your original integrand. But this type of substitution doesn't always work. Sometimes we'll actually want to do the opposite type of substitution, and that's what you see up above here. Suppose you have the integral of some function f of x dx. You can turn that into a composition type of function by making the substitution x equals g of t. And if x is equal to g of t, then dx would be equal to g prime of t times dt. And you can see if we substitute g of t in for x and g prime of t times dt in for dx, we get this integral. But why would you ever want to do this? Well, sometimes, even though the appearance here is that we end up with a function that is much more complicated, sometimes this will actually be better than what we start with. It all depends on the situation. So let's go ahead and get into the guidelines for how to make trigonometric substitutions, and then we'll do some examples. So here we have a table of trigonometric substitutions. There are three basic types of substitutions that you will make. And what you really want to focus on here is the expression that you'll have in your integral and the type of substitution that you will make. The rest of these points are important points about domain, etc. But this part right here is what you need to remember. So if you have the square root of a squared minus x squared, the substitution that you want to make is to let x equal a times the sine of theta. And this is actually an example of the first problem that we looked at, where we looked at the expression square root of 9 minus x squared. You can think of 9 as being 3 squared. And so you can see that this fits the pattern of the square root of a squared minus x squared. And the substitution to make is to let x equal a times the sine of theta. And that's what we did just a few minutes ago. I let x equal to 3 sine of theta because in this particular example, a is 3. Well, what if you had the expression square root of a squared plus x squared? Then the substitution you would want to make would be x equals a times the tangent of theta. And finally, if you had the square root of x squared minus a squared, the substitution you need to make is x equals a times the secant of theta. Now, why is it a different substitution for each of these? Well, it all depends on the Pythagorean identity that you're going to use to simplify your expression. So depending on the order of the subtraction of a squared and x squared, or if you're adding a squared and x squared, you're going to use a different substitution because it takes a different identity to simplify each one of those. To put it bluntly, you need to memorize these three cases. So in our first example, we would like to integrate the square root of 9 minus x squared divided by x squared. So I'm going to focus on the fact that I have 9 minus x squared. And you can think of that as 3 squared minus x squared. And in this situation, the trigonometric substitution to make is to let x equal 3 times the sine of theta. If that's true, then dx is going to be 3 cosine of theta d theta. And now we're just going to replace x here and here with 3 sine of theta. And we'll replace dx with 3 cosine of theta times d theta. So this integral becomes the integral of the square root of 9 minus 3 sine of theta quantity squared divided by 3 sine of theta quantity squared, and then times dx is 3 cosine of theta d theta. It's very important that you don't simply replace dx with d theta. You have to remember to compute it based on your substitution. And then that whole expression replaces dx down here. Okay, so now we're just going to simplify these expressions. So in the numerator, we have the square root of 9 minus 9 sine squared divided by 9 sine squared times 3 cosine theta d theta. Now, if you want, you can take these expressions outside and simplify them. So the square root of 9 minus 9 sine squared, we did this just a few moments ago. If I factor out the 9, we get this. And then if we remember that 1 minus sine squared is cosine squared, we get that. And then we just take the square root of each part. And this is going to be 3 absolute value of cosine. Now, it turns out in these substitutions, you can ignore the absolute value based on the domain of theta. Okay? So in this particular case, theta is always going to be an angle between negative pi over 2 and positive pi over 2, and that means that cosine of theta will always be positive for those values of theta. So the bottom line is we're just going to simplify this to be 3 cosine of theta. So this whole expression right here is going to be replaced with 3 cosine of theta. So what we have here is the integral of 3 cosine of theta divided by 9 sine squared of theta times 3 cosine of theta d theta. Now if we simplify this, I want you to notice that we have 3 times 3 here, which is 9. So those are going to cancel out with the 9 in the denominator. And we end up getting the integral of cosine times cosine, which is cosine squared, divided by sine squared, d theta. And then notice that cosine divided by sine is cotangent. So we can change this to cotangent squared. Now, how do we integrate cotangent squared? So we have to think about our trigonometric integrals now. We're going to use an identity. Cotangent squared of theta is the same as cosecant squared of theta minus 1. Now, why bring in that identity? Well, because the integral of cosecant squared of theta, we know what that is, right? Do you know what it is? Well, we know the integral of secant squared is tangent, so the integral of cosecant squared is actually negative cotangent of theta. And then don't forget, you also have to take the antiderivative of negative 1 right there, and so that's going to be negative theta. But this isn't our answer, because our original problem was a function of x, and we made a substitution. The substitution that we made was to let x equal 3 times the sine of theta. Or to put that differently, we can say sine of theta is equal to x divided by 3. Now, let's think about what this means in terms of a right triangle. If I have a right triangle with an angle theta here, if sine of theta is x divided by 3, that means the opposite side of theta would be x and the hypotenuse would be 3. And then we can solve for the missing side here, which I'll call a temporarily, by using the Pythagorean theorem. We know that a squared plus x squared is equal to 3 squared, and so a squared is going to be 9 minus x squared, and that means that a will be the square root of 9 minus x squared. So we can replace a here with that value. And the whole reason I'm doing this is because if you come back to our answer here, we have negative cotangent of theta. Well, what is cotangent of theta? Well, if you look at the triangle here, we know that cotangent of the angle theta is equal to the adjacent side divided by the opposite side. So it's adjacent over opposite. And so negative cotangent of theta is negative square root of 9 minus x squared over x. And then we have minus theta. But what is theta? Well, let's focus in here. We know sine of theta is x over 3. So if we take the inverse sine of both sides, we get the inverse sine of the sine of theta is equal to the inverse sine of x over 3. And what happens is these cancel out, and we get theta is equal to the inverse sine of x over 3. And I can replace the theta here with that. And then once I've done that, I have my antiderivative, so I can just put my constant of integration. Suppose we wish to find the area enclosed by the ellipse x squared over a squared plus y squared over b squared is equal to 1. And here we have a graph of that ellipse. To find the area of the entire ellipse, all we need to do is find the area in the first quadrant here, and then just multiply that quantity by 4. So let's say that A represents just this area. To calculate that area, a is going to be the integral from 0 to little a, right, because those are your limits on the x-axis, of your function, which I'll just call f of x for now. So f of x is this function right here. So to get f of x, we need to take our equation here, and we need to solve it for y. Now, there's a couple of different ways to solve it for y. What I'm going to do is just multiply both sides of the equation by a squared b squared. What this is going to do is get rid of the fractions. So here a squared cancels with the a squared there, and we're going to get b squared times x squared plus, and then when you multiply here, the b squared cancels, and you get a squared times y squared is equal to a squared b squared. Now to solve for y, next I'm going to subtract b squared x squared from both sides. That gives us a squared y squared is equal to a squared b squared minus b squared x squared. Now I would like to point out that you can factor out a b squared on the right-hand side. Let's go ahead and do that. And then to solve for y, we're just going to divide by a squared on both sides, which gives us y equals b squared over a squared times the quantity a squared minus x squared. And the last step is we'll just take the square root of both sides. And this is going to give us y equals plus or minus. Now, the square root of b squared over a squared is just b over a. And then we have the square root of a squared minus x squared. And we're only going to take the plus side of that because the plus represents the function above the x-axis. The minus would represent the function down here. So our function f of x over here that we're going to put in the integral is b over a times the square root of a squared minus x squared. So now our area is going to be the integral from 0 to a of your function b over a times the square root of a squared minus x squared times dx. Keep in mind that the b over a here is a constant, so we can actually factor that outside of the integral, like so. And now we're just going to focus in on that integral. This is going to be a trigonometric substitution where we let we let x be equal to a times the sine of theta. Dx will be a cosine of theta, d theta. And this integral becomes b over a integral square root a squared minus x squared is going to be this thing squared. So a sine of theta quantity squared times dx. Dx is a cosine of theta d theta. Now let's go ahead and change our limits since we have a definite integral. So when x is equal to 0, we get 0 equals a sine of theta. And we know that this means theta is 0 because we know that sine of 0 is 0. And then if x is equal to a, the upper limit, this is going to give us a equals a sine of theta, which is the same thing as saying sine of theta equals 1. And that happens when theta is pi over 2. Okay, so now let's go ahead and compute the value here. So this becomes b over a integral from 0 to pi over 2. Let's simplify that radical. We have the square root of a squared minus a squared sine squared. You can factor out the a squared on the inside of the radical. Use a trig identity. 1 minus sine squared is cosine squared. And then we'll take the square root of a squared and the square root of cosine squared. And this is going to give us a cosine of theta. Remember, we don't need absolute values. So we have a cosine of theta. That's the radical here. But then we have another a cosine of theta over here, and then d theta. Now, the a on the outside will cancel out one of the a's on the inside. The other a I'm going to factor out, so that's going to be a times b, integral from 0 to pi over 2, and then cosine theta times cosine theta is cosine squared of theta, d theta. Now, how do we do that integral? Well, you have to think back to the previous section. When you have the integral of cosine squared, you have to use the half-angle identity. We know that cosine squared of theta is 1 plus cosine of 2 theta, all divided by 2. So we have AB over 2. I'm going to factor this out. Integral from 0 to pi over 2, 1 plus cosine of 2 theta, d theta. Now we take our antiderivative. Antiderivative of 1 is just theta, plus the antiderivative of cosine of 2 theta is 1/2 sine of 2 theta, and this goes from 0 to pi over 2. So next, we're going to go ahead and plug in pi over 2 for theta. And then we'll plug in 0 for theta. Let's see here. It's 2 times 0. There we go. And then we need to remember that sine of 0 is 0. When you plug in 0 here, you get 0. 2 times pi over 2 is pi, and the sine of pi is 0. So all of those cancel out. And we end up getting AB over 2 times pi over 2, which is equal to pi AB over 4. Now remember, this is the area of this part of the graph. So the total area of the entire ellipse is going to be 4 times the answer that we just got. And the answer we just got was pi times a times b divided by 4. And so the total area of the ellipse is pi AB. In the next problem, we have a slightly different trigonometric substitution to make. Notice that we have the expression x squared plus 4. So that is like x squared plus a squared. And in this situation, we are supposed to let x be equal to 2 times the tangent of theta. Now, why 2? Well, it's because 4 is the same as 2 squared, right? So when you're making the analogy between what you have and x squared plus a squared, you can see that a would need to be 2 for this to happen. All right, so let's go ahead and find dx. So dx will be 2 secant squared of theta, d theta. And when we plug it in, our integral, we have a 1 on top. X squared will become 2 tangent of theta quantity squared. And then we have the square root of x squared again, so 2 tangent of theta quantity squared plus 4. And then times dx, which is 2 secant squared theta d theta. Now, when your dx is off to the side like this, it's actually more convenient to go ahead and just put that in the numerator of the fraction. So this becomes the integral of 2 secant squared of theta d theta divided by 4 tangent squared of theta is what we get here. And then we have the square root of 4 tangent squared of theta plus 4. So let's work on simplifying that radical there. Square root of 4 tangent squared theta plus 4. We're going to factor out the 4. Use an identity, tangent squared of theta plus 1 is secant squared of theta. Separate the radical. Square root of 4 is 2, and the square root of secant squared, well, technically it's the absolute value of secant, but once again, you can leave off the absolute value for domain reasons. So this whole radical expression here becomes 2 secant of theta. So then our integral becomes the integral of 2 secant squared of theta d theta over 4 times tangent squared of theta times 2 secant theta. All right, so now we're going to cancel what we can. 2 divided by 2 cancels. Secant theta here and secant theta there cancel. And we end up with the integral of secant of theta over tangent squared of theta. And then the 4 in the bottom, we'll pull that out as a 1/4 on the outside of the fraction. And now how do we integrate this? Well, this integral here doesn't actually follow any of the guidelines for secants and tangents. So what I'm going to do is just simplify the expression using sines and cosines. So if we have secant theta divided by tangent squared of theta, secant is 1 over cosine, and tangent squared is sine squared over cosine squared. And so we can rewrite this as 1 over cosine times cosine squared over sine squared. And then cosine here cancels out with one of those cosines. And so this whole expression simplifies into cosine of theta over sine squared of theta. And I don't know about you, but I always prefer to have sines and cosines instead of secants and tangents. They just seem to be easier to deal with. And this is no exception here. Now, all we have to do to finish this is make a u substitution. I'm going to let u equal sine of theta. Du will be cosine of theta d theta. And this becomes 1/4 integral of du over u squared, or 1/4 integral of u to the negative 2 du. And when you take the antiderivative of u to the negative 2, you get u to the negative 1 divided by negative 1, which is the same as negative 1 over u, and then don't forget the 4 there. So negative 1 over 4u, and that is negative 1 over 4 times u is sine of theta. And then finally, we have to say, but what is sine of theta? So for this, we have to go all the way back to the beginning where we made our substitution. And we're going to draw a right triangle to represent the original substitution here. So when I draw that triangle, here's my right triangle. Here's theta. We know that x equals 2 tangent of theta. That's the same thing as saying tangent of theta is equal to x divided by 2. Tangent is opposite over adjacent. And so this would have to be x, and this would have to be 2. I'll call this missing side a, and we know that 2 squared plus x squared must be equal to a squared. So 4 plus x squared is a squared, and if we take the square root of both sides, a will be the square root of 4 plus x squared. And so we can put that in here. And now what we were asking down here, right, our answer is negative 1 over 4 times the sine of theta. So we just need to know what is the sine of theta. So let's go back up to that triangle. In this picture, sine of theta is opposite over hypotenuse, and that is x over the square root of 4 plus x squared. Or you can think of that as x over the square root of x squared plus 4. So I'm going to take this expression now down here and plug it in. So this is negative 1 over 4 times x over the square root of x squared plus 4. And this is going to get flipped, into the square root of x squared plus 4 over x. And if I multiply these together, I end up with our final answer here. So you have to be really patient on these problems. You have to make your substitution, do the integration. Sometimes you'll have an additional substitution to make, like we did here with the u substitution. But you just have to retrace your steps. So once I did the u substitution and I got my answer here, I put back in the u was equal to sine of theta. And then I said, but what is sine of theta equal to? So I had to go all the way back to the original substitution and make a triangle, and then come back down and substitute that in, and then simplify the result. So it really just takes patience, perseverance, and most importantly, you can't make any mistakes while you're doing this. So you got to be really diligent and careful not to make any little mistakes. All right, so this next problem here, you can see that you have the square root of x squared plus 4 again. So this will take the same trigonometric substitution. We'll let x equal 2 tangent of theta, and dx will be equal to 2 secant squared of theta d theta. And you could certainly make this substitution. However, I want to point something out to you. We don't need trigonometric substitution to do this problem, right? Take a look at the problem. You have the integral of x over the square root of x squared plus 4. We can use regular u substitution on this problem. If I let u equal x squared plus 4, du will be 2x dx. And if I put the 2 in here and the 1/2 on the outside, this becomes 1/2 the integral of du over the square root of u, or 1/2 integral of u to the negative 1/2 du. Take the antiderivative, we get u to the positive 1/2 divided by 1/2. Invert and multiply, and you end up getting the square root of u, which is the square root of x squared plus 4 plus c. So although you can use trigonometric substitution, and if you want, go ahead and pause the video and make this substitution and see if you can get the same answer. I think what you'll find is that the u substitution is a little bit easier. So what I'm saying is, don't throw out the old just because you learned a new method. The old methods still work when they work. So what we need to do is make sure that we're remembering all of the old methods as we learn these new methods. All right, so in the next problem here, we have the integral of dx over the square root of x squared minus a squared. So this is the case where we're going to let x be equal to a times the secant of theta. And so dx will be a times secant theta, tangent theta, d theta. And our integral becomes the integral of all of this on top. And then in the denominator, we have the square root of x squared, which is going to be a secant theta quantity squared minus a squared. And so let's go ahead and work on this radical here. This is going to be the square root of a squared secant squared minus a squared. And then we can factor out the a squared inside the radical. And that gives us secant squared minus 1. And we know that secant squared minus 1 is tangent squared. And then we'll take the square root of each of those. And that is going to give us a times tangent of theta. And so this integral becomes, same numerator, and in the denominator, we just have a tangent of theta. And so this a cancels out, and this tangent theta cancels out, and this integral gets to be quite simple. Integral of secant of theta d theta. But what is this integral? So we actually talked about this in a previous video. This is the natural log of secant of theta plus tangent of theta plus c. But then, of course, we need to come in here and replace secant theta and tangent of theta because our original variable was x. So if we go back to the original substitution, we know that x is equal to a secant of theta, or secant of theta is equal to x divided by a. And if I draw a picture of a right triangle representing this, we know that secant is the hypotenuse over the adjacent. So x will go here, a will go here. And if you solve for the missing side using the Pythagorean theorem, you're going to get the square root of x squared minus a squared. So what is tangent of theta? Tangent of theta is the square root of x squared minus a squared divided by a, right? Because tangent is opposite over adjacent. And so now our answer here can be rewritten as the natural log of secant of theta, which is x over a, plus tangent of theta, which is square root x squared minus a squared over a plus c. Now you could leave your answer like this, but let me show you another way to write the answer. We have the natural log of the absolute value of x plus the square root of x squared minus a squared all over a. And then we can use properties of logarithms to write this as the natural log of the absolute value of the top minus the natural log of the absolute value of the bottom. But if a is a constant, the natural log of a is a constant, and plus c is a constant. And so negative natural log of a plus a constant is just a new constant. So we can express this as the natural log of the absolute value of x plus the square root of x squared minus a squared plus c1. And that's a little nicer answer than the answer up here. Now both answers are correct, but this one's just a little bit more simple. In this next example, we have a slightly different expression here. We have 4x squared plus 9 inside of our parentheses. So let's talk about how to deal with that. So when you have something other than just x squared, what you want to do is express it as a perfect square if you can. So 4x squared is the same as 2x quantity squared, just like 9 is 3 squared. And then when you make your substitution, normally you would just let x be equal to 3 tangent of theta here. But because we have 2x there, we have to have a 2 in front of our substitution as well. Now that's the same as x is equal to 3 halves tangent of theta. And if that's the case, then dx would be 3 halves secant squared of theta d theta. Now let's go ahead and plug these in. So we have the integral, and we'll have to change our limits here in just a minute. We've got x cubed, which is going to be this thing cubed, divided by, and then now we have 4x squared, so that's going to be 4 times 3 halves tangent of theta quantity squared plus 9 to the 3 halves. And then don't forget your dx, and dx is 3 halves secant squared theta d theta. Now what about the limits here? When x is 0, if I plug in x equals 0 here, we get 0 equals 3 halves tangent of theta. This means that tangent of theta is 0, which means theta is 0. So our lower limit is going to be 0. The upper limit, 3 radical 3 over 2 for x. This means that 3 radical 3 over 2 is going to be equal to 3/2 tangent of theta. Multiplying by 2 on both sides and dividing by 3 on both sides gives us tangent of theta is equal to radical 3. And this happens when theta is pi over 3. So our new limits are going to be 0 and pi over 3. Now let's go ahead and work on the integral here. We've got a lot of simplifying to do. When you cube this, you're going to get 27 over 8 tangent cubed of theta times 3/2 secant squared of theta d theta, all divided by, now on the bottom here, got to be careful. When you square this, you get 9/4 tangent squared, but then it's multiplied by 4. And so the 4 is going to cancel out there, and then we have plus 9. So what I've got there in total is 9 tangent squared of theta plus 9 to the 3/2. All right, let's continue to simplify. 27 times 3 is 81. Let's pull that out of the integral. 8 times 2 is 16. Let's pull that out of the integral. We have tangent cubed theta secant squared theta d theta. And in the denominator here, we have 9 times tangent squared of theta plus 1, quantity to the 3/2. That is 9 secant squared of theta, quantity to the 3/2. So we are going to take the square root of 9 and the square root of secant squared, and then we're going to cube it. So that is going to be 3 cubed, which is 27, and then secant cubed. Okay, now let's cancel what we can. Secant squared is going to take out 2 of those secants. 27 is going to go into 81 3 times. And so it looks like we have 3/16 integral from 0 to pi over 3. And we have tangent cubed of theta divided by secant of theta d theta. Okay, so next we're going to simplify this expression here. We have tangent cubed theta over secant of theta. This is the same as sine cubed over cosine cubed divided by 1 over cosine. And that is sine cubed over cosine cubed times cosine over 1. And this cosine will cancel out one of those cosines. And so that becomes sine cubed over cosine squared. So let's go ahead and bring that into the integral here. We have 3/16 integral of sine cubed theta over cosine squared theta d theta. All right. Now, the technique to use here, since we have an odd power of sine there, is I'm just going to pull out one of those signs. So we're going to have sine squared over cosine squared times sine of theta d theta. And so what I'm thinking is this I want to be my du. And for that to happen, I need to let u be equal to cosine, right? Because if u is cosine, du would be negative sine. And of course, the negative is no big deal. I can put a negative on there and compensate for that, but putting a negative on the outside. And so if I do all that, this becomes negative 3/16 integral. Now the bottom is going to be u squared. Then we have du over here. But what is sine squared? So we need to remember that sine squared is 1 minus cosine squared. And if u is cosine, then this becomes 1 minus u squared. And then we got to change our limits again. So if theta is equal to 0, then u is going to be the cosine of 0, which is 1. And if theta is equal to pi over 3, u will be the cosine of pi over 3, which is 1/2. So now it all comes down to doing this integral. Now one thing I could do here is I could make this a positive and just switch these limits. That's a property of integration. So we'll have positive 3/16 integral from 1/2 to 1. And now I'm just going to separate that into 1 over u squared minus u squared over u squared. And so that becomes 3/16 integral of u to the negative 2 minus 1. And this becomes u to the negative 1 over negative 1. So I'm taking the antiderivative now, minus u. And we get 3/16. This is going to be negative 1 over u minus u from 1/2 to 1. So let's go ahead and plug it in here. We have 3/16. When you plug in 1, you get negative 1 minus 1 minus, when you plug in 1/2, negative 1 over 1/2 is negative 2. And when you plug in 1/2 into the second part, you get minus 1/2. So we have 3/16 times negative 2 minus negative 5 over 2. So this is 3/16 times negative 2 plus 5 over 2, which is 3/16 times 1/2, which ends up giving us 3 over 32. In our final example, this one's a little bit tricky. You can't immediately use a trig substitution. What you need to do here is take the expression 3 minus 2x minus x squared, and we need to write it as a perfect square. So let me rearrange this to say it's negative x squared minus 2x plus 3. I'm going to factor the negative out of the first two terms. And then I'm going to complete the square here by adding 1. Now, when I added 1, I really subtracted 1 because there's a negative out here. So I'm going to add 1 over here to compensate for that. And then this is just negative x plus 1 quantity to the second power plus 4, which is the same as 4 minus x plus 1 to the second power. So what does that mean? Well, it means that our original integral now can be rewritten with the radical on the bottom having this expression on the inside instead of the original expression. And this allows us to use a trig substitution. So what I can do here is I can let x plus 1 be equal to 2 sine of theta. And then if I take the derivative, dx will be 2 cosine of theta d theta. And then this integral becomes, in the denominator, 4 minus x plus 1 squared is this thing squared. So 2 sine of theta squared. X on top, we have to solve for x here. So x is going to be 2 sine of theta minus 1. And then dx is 2 cosine of theta d theta. And so now I just need to simplify. We have the integral 2 sine of theta minus 1 times 2 cosine of theta d theta. In the denominator here, we have the square root of 4 minus 4 sine squared. That is the square root of 4 times 1 minus sine squared, which is the square root of 4 cosine squared, which is 2 cosine of theta. So that worked out nicely. Now we can cancel 2 cosine theta top and bottom. And we get the integral of 2 sine of theta minus 1 d theta. And this is straightforward, nothing tricky here. we have 2 times antiderivative of sine is negative cosine, minus the antiderivative of 1 is theta. And so we have negative 2 cosine of theta minus theta. And this is our answer, except that we have to put back in our original variable. So we've got to go back up to the beginning. Right here, we said x plus 1 is equal to 2 sine of theta. That's the same as sine of theta is equal to x plus 1 divided by 2, which, by the way, means theta is going to be inverse sine of x plus 1 divided by 2. But then if I draw a triangle of the relationship here, representing the relationship, sine of theta is opposite over hypotenuse. This side right here is going to be the square root of 4 minus x plus 1 squared, which of course was our original radical at the beginning of the problem. So now to finish it, I just need to know, what is cosine of theta? Well, cosine is this divided by this. And so that is the square root of 4 minus x plus 1 quantity squared over 2. And of course, we could rewrite this using the original expression. So our answer is going to be negative 2 times cosine of theta, which is this expression, and then minus theta, but theta is inverse sine of x plus 1 divided by 2. So now if I just cancel out the 2's here, I get negative square root 3 minus 2x minus x squared minus the inverse sine of x plus 1 over 2 plus c. And that concludes this video lesson.